All right, so lesson 4, limits approaching infinity. So if you guys remember in the last lessons, right, we were looking at some graph. Maybe the graph did something like this, and then let's say at the point 4, right, we were figuring out, okay, if it's approaching it from the left and from the right, what value is it actually going toward, right? And that's the limit, right? So sometimes it didn't actually work out because from the left and from the right, maybe it was approaching that value, whatever it was there, but maybe it was a hole and the point was actually down here, right? So even though the point wasn't necessarily on the graph, you could still say that the limit was approaching that value, right? Like that hole, right? So anyway, so that was limits approaching some number. Now what we're going to do is we're going to start doing limits to infinity. And what that means is, let's say this graph like here, right? Let's say we had a graph that went up and then there was some horizontal asymptote there, right? And let's say that I know that horizontal asymptote is at the point 5, right? Is where that line would be. Well, you can probably see even from the graph here, as x went infinitely far to the right, as x starts approaching infinity, what do you think the y would be getting closer and closer toward? 5. That's really what this lesson is going to be about, right? As you go closer and closer to infinity, what number do you start getting closer and closer to, right? So let's look at this example. So consider the function 1 over x, okay? So as x gets larger and larger in this case, right? You're going 1 divided by a bigger and bigger and bigger number. What are you approaching? 0, right? So this thing should be approaching 0, which actually still makes sense even with with this graph, right? You guys remember this graph looked like this, right? So as we get closer and closer to infinity, we're getting ever closer to 0. Our graph is approaching the line 0. That's an asymptote, right? So that makes sense. It won't ever reach 0, right? But anyways, that's kind of the idea here. So one thing to kind of note is that when I'm saying that when we approach infinity, infinity is kind of a weird concept. It's actually not a number. It's not like a number, like a really, really big number. That's kind of a misconception. People will think, if I keep going, like just the biggest number I can find is infinity. It's actually not a number at all. Infinity is a concept. It's something that you're never going to get to. It's like it's not a specific number. It's without bound. It just keeps on going forever, right? So it's not like an actual number value, okay? But we can still use it in math, right? So for each of the following functions, determine the limit as x approaches infinity. So let's say for this first one, right? So if we had the limit, so we'd write it this way. We'd say the limit as x approaches infinity of, and I'll just say f of x. Okay? So now if we have a picture of it below, right? So what do you guys think? As we're approaching infinity, that means we're going farther and farther to the right, infinitely far to the right. What are we approaching here? Infinity. Yeah, you're approaching infinity. Like the y value is approaching infinity. But this relates to what I was just saying at the top there. That is true. It is approaching infinity. But technically when we're talking about a limit, when we say we're approaching a number, right? We should be approaching a number at this case. So this is actually like a weird thing in math. And if you start Googling these things, different math professors would say that the limit as x approaches infinity of that function, they'd say it's infinity. And others would say, actually, it does not exist. And technically, it just doesn't exist. So if we're technically talking about the limit here, it doesn't exist at all, right? But it's kind of useful for us to say it's approaching infinity because we can see it's approaching infinity, right? So when you guys do your My Open Math questions, you'll see that the answer would accept either or when you were doing it. It would be like does not exist or infinity in that case. Okay. So the next one, what do you guys think? What are we approaching here?
0.
Yeah, so in this case, the limit, oh, that was messy, as x approaches infinity would be equal to 0. Oh, of f of x, sorry. Now, the other thing that our textbook and doesn't, it always does it this way. We would always say as x approaches infinity, right? And this makes sense. As x approaches infinity, then we're getting ever closer to 0, right? As we're coming down. Now, technically, you could also say, what's the limit of f of x as x approaches negative infinity? And what would that be? It would still be 0, right? But it's going the other way. But they're not always the same number, right? Like you'll actually see, like when we get down to d, they won't necessarily be the same number. But as far as we're concerned in high school calculus, we're always going to be doing to the right. Like for this lesson anyway, we'll throw in like lessons later on where we'll be going to the left and the right. But for now, we're always going to be going like positive infinity in our questions. Okay, so this one, just looking at the graph here, that limit would be 3, right? Is what we're going to be approaching. What about this one? The limit as x approaches of f of x as x approaches infinity. What's that going to be? 0, yeah. And then what about this one? The limit as x approaches infinity of f of x. So again, you could say that this was infinity, right? It's going infinitely far up, or does not exist. Okay, so in summary, we actually talked about this in 30-1 as well, right? Where, do you guys remember when we were doing pretty much like our asymptotes, like whether or not the thing went forever or like where was the horizontal asymptote? I actually showed you guys this little method before, so this should actually be a little bit of review. But in general, if you look at this function and we want to figure out what the limit of f of x would be in this case, if the top, right, if the top is greater than the bottom, then in this case, what do you think the limit would be? So if the numerator was greater than the denominator, it'd be approaching infinity or does not exist, right? It'd be like either one. And that actually kind of makes sense, right? Because if I, like what this means is I've got 3 in the bottom and I've got like, you know, a very, very, very large number in the top. So this thing is going to be getting farther and farther away. Like if you graph this thing, right, it's going to be getting farther and farther and farther away. This one would, you know, be a straight line, but it's getting farther. It's going toward infinity at the top, right? So that makes sense that I'm not going to be able to have a limit there. So if the top's greater than the bottom, you'd say, you know, there's that the limit, we should probably write it out, as x approaches infinity of f of x, you would say it does not exist, or infinity, right? Okay, now if you have a rational function where the degree of the top is less than the degree of the bottom, right? So in this case, the top is less than the bottom, right? Then what we're going to have here is, well, what are we going to have? What do you guys think? Yeah, it's going to be approaching 0, right? Because this number on the bottom is growing a lot faster than the number on top, right? So in this case, we would have the limit as x approaches infinity of f of x would be equal to 0. Now, that was the example I used there, but this would also be true if I would have had, like, let's say 4x squared over 3x, right? And it's the same concept here that you can imagine if I threw a very, very large number in for x, right? So like 1 million, right? I threw 1 million in for x on the top and 1 million in for x on the bottom. The fact that I'm squaring this thing means that it's rising a lot quicker, right? So that means that the top is growing a lot faster than the bottom is. So same thing, this graph would be getting farther and farther and farther away from 0, right? It's approaching infinity in that case. Okay, so now this one. So this was where we figured out our horizontal asymptotes in 30-1, right? If they're equal, right? If the degrees on these rational functions are equal, do you guys remember what we did here? Yeah, it was just the coefficients of the numbers out front. And I'm going to show you 2 different ways of thinking about this too, where you can think about it the same as we did last time. If I threw like a really large number in for x, right, into both of those, then, you know, you might be tempted to say, well, what about this +1 on the bottom, right? The +1's got to be contributing something. But really not, right? Like once I start throwing numbers in that are like close to infinity, right? Like just really, really, really big numbers, that 1 is just incredibly insignificant, right? It doesn't really matter at all. So you could almost think about these things canceling each other out, and all you'd be left with is the coefficients out front, right? And that would also be true if it would have been something like 3x squared plus 2x over, let's say, 4x squared or something, right? These x squareds trump the x, right? Those things are like when you get really, really big numbers, even when I have like, you know, a really, really big number there, it's insignificant when I'm actually squaring these things, right? So again, that doesn't even matter. It really just comes down to these two things. You know, we cancel each other out and you'd be left with the coefficients out front. So these are super easy to kind of look at and figure out if you know what you're doing. The other way that we should look at this, just to make sure that this all works out, is if we were to take the limit of this. So we'd write, you guys will need to do this too. So if you were to write the limit as x approaches infinity of, I'll just write that again, 3x squared over x squared plus 4. So what we can do here is we can, to find the limit algebraically, like technically the way we should be doing this, is we will divide every term by the highest degree, then apply the rules from the first two cases. Okay, so what I mean by that, the highest degree here is x squared. So what that means is we're actually going to divide everything. We're going to rewrite this as the limit as x approaches infinity of 3x squared, and then this is like we're going to do what we said there, the highest degree. So we're going to divide everything by, so 3x squared divided by x squared over, and then this term, so x squared divided by x squared plus 1 over x squared. Do you guys see that I didn't actually change the equation there? Because we just divided everything by x squared, so it didn't actually do anything. But what this does allow us to do is now, when we take the limit of this, right? This is actually the same thing as taking the limit of x, or as x approaches infinity, of each of these pieces, like the limit of this, and the limit of this. So it's like the limit as x approaches infinity of 3x squared over x squared over the limit as x approaches infinity of x squared over x squared plus the limit as x approaches infinity of 1 over x squared. Yep.
Shouldn't that 1 be a 4?
Did I? Oh, you know what? Oh yeah, I called it 4 in here. Okay, let's stick with a 4. We'll just do, yeah, that's what my notes are anyway. So then, oh yeah, so that should be a 4 then, yeah. Okay, so now if that's the case, right, if I'm looking at just this top part, using the rules from above here, if I've got, you know, x over x, those really, you know, cancel each other out, don't they? So in this case, this is going to be, right, that first part there would just be 3, you know, x squared over x squared. Those cancel. So this is really just 3. The bottom here would be just 1, right? You can kind of see where that's going. So that would be equal to 1. And then this part here, what would this become? The limit as x approaches infinity of 4 over x squared.
0.
Yeah, it'd just be 0, right? So in the end here, we can kind of see all of that work to say that it would be 3 over 1 plus 0. So 3. Does that make sense? And we could have actually seen that right from the beginning, couldn't we? It would have been 3. So this is kind of like a lot of times like in these calculus courses, we do that, and it's just like kind of the proof of it, right? So you guys are probably rolling your eyes being like, yeah, why did we do all that work when you just showed us that we didn't need to do all that? I do want you to see that that's the reason this is all kind of working out too, right? Okay. So the next example for limits to infinity, if we have an exponential function, right? So something like f of x is equal to b to the power of x, right? So if we remember back to 30-1, like our exponents unit, if b is less than 1, let's just even think about this, right? If our b value is less than 1, do you guys remember what kind of graph they gave us? Yeah, down. Yeah, and it said decay. Yeah, so that'd be a graph kind of like this, right? What does that look like? That's approaching. Yeah, that's going to be our 0, right? So that's going to be a decay graph, and it's going to approach 0. Okay, and then you probably read my mind here. What if b is greater than 1? Growth, yeah. So that's going to approach infinity. Which you would say, it's the last one to be equal to 0, and this one to be does not exist. Oop, does not exist. All right, so let's evaluate a few. So these won't take very long. Evaluate each of the following limits if they exist. So looking at that top one there, what do you guys think? Yeah, the top is growing faster than the bottom, isn't it? So you could do that whole method that we did. We could divide every one of those by x squared, right, the top and bottom, and take the individual limits. I'm kind of lazy right now, though. Let's just use the other method. We'll just say the top's growing faster than the bottom, so it does not exist. Okay, so for B, what do you guys think?
0.
Just careful on this one, though. They were trying to be tricky. We could rewrite this a little different, right? Let's say the limit as x approaches infinity of negative 5x squared plus x. And then on the bottom, we've got 3x squared. Can you guys see it now?
They're equal.
Yeah, they're like the exponents are equal. So what would the limit be in this case?
-5/3.
Yeah, negative 5 over 3, right? So just the numbers out front. So negative 5 over 3. Okay, what about C? Yep.
Is it just 0?
0, yeah. How come it's 0?
Because it's decaying exponential function.
Yeah, it's decaying, right? Our B value in this case, right? Of 3 over 8, that's less than 1, so this thing is going to be getting smaller over time. So this thing would be equal to 0. Okay, and then what with this one? 0? Yeah. Yeah, the bottom's growing faster than the top would be, so that would, again, would be 0. Okay, what about this one? This one's kind of weird. So negative 3x.
Wait, why was C 0?
See? Okay, and this one, it's because it's 3 over 8, right? So it's like you've got a decimal that's between 0 and 1 to the power of an exponent. So that graph, if you think about it, would be like a decay graph.
Okay, yeah.
Going down like that.
Yeah.
If that number would have been greater than 1, then it would have been going up like that.
Okay.
Yeah. Okay, the limit of negative 3 to the power of x.
Well,
Yeah, that's what I was saying. It's kind of a weird one, right? Because a negative number, and I'm going to a power, right? So if this was 2, that would be a positive number. If it was 3, it'd be a negative number. If it was 4, it'd be a positive. So this one's kind of jumping all over the map. Doesn't really approach anything, does it? Yeah, so in this case, it just does not exist either. So now this one, what I recommend doing, we can see, you should expand these, just to make sure you can see what the coefficients actually would be here. What's that?
1/4.
Yeah, exactly. So if we expanded this would be n squared plus n over, and then 4n squared minus 4n plus 1. And again, we can see our coefficients out front there would just be 1 over 4. Okay, this one's kind of weird. We can use our same logic though, right? From the last one. What do you guys think for this one? As we approach infinity, just thinking about like how fast the top's growing, how fast the bottom's growing. What do you think on this one?
Zero.
0, yeah. The bottom is growing faster, right? Because this is like the square root. Again, I can just kind of like ignore the -1 because it's going to be so insignificant in this case, right? But if I have my x in there and that's a very, very large number, it's always going to be smaller than the number on the bottom, right? And the bottom's going to be growing so much faster. So again, we can say that this will be 0. Now the last one here, well, it'll actually be the same answer either way. If I put brackets around the whole thing and say that this was the limit as x approaches infinity of the whole thing, or if I had it written like this, where it was just that, it'll end up being the same number. Let's see why. So if I do the limit of the whole thing, that would be the same thing as the limit as x approaches infinity of 3,000 over x squared minus the limit as x approaches infinity of pi, just pi. So if I did that, we can just kind of do it piece by piece, right? So the first part, what would the limit of the first one be there? 0, right? So this would be 0 minus, and then what's the second one? As x approaches infinity of pi, what is that approaching? Won't be 0. There actually is no x, pi. There actually is no x value here, right? So so the limit of a constant is just a constant, right? So this would just be pi. So in the end, this would be negative pi. And that would have been the same. So that's what I was saying before. It wouldn't have mattered, right? Because if I found the limit of this and then minus pi, that would have been the same answer. So either way you look at that one, that would have been the same answer. So that's it. That's that lesson.